Hello guys and welcome to another video. This is actually, I think, the first video on my channel that is not a math video. This is actually a chemistry video, which I know most of you will not find interesting, but I just found this problem super fun and I love chemistry, so I decided to make a video on it. So this is an inorganic scheme problem, which means it's a problem where they give us a bunch of different unknown compounds and tell us how they react, and we have to figure out what those compounds are step by step. This is from Edward Jin. You can go check out his website to find the problem. He's absolutely goated as well. And I have the whole problem shown right here. So this is all the information we're given for the problem. In addition to, obviously, you could have like a periodic table and a calculator, of course. So let's go ahead and jump right into it. So either pause here and try the problem by yourself, or go ahead and look it up on Edward Jin's website. It's called Nobility. So we're going to go ahead and take this step by step, and we're going to start at the top and also use some of this as well. And then eventually we're just going to go through each reaction one by one and figure out all the products. So the first thing we notice is that both gases X and Z, gas X is in paragraph 1 and gas Z is in paragraph 2, they're described as thought to be chemically inert, which pretty much immediately tells us that they're going to be noble gases, because those are the only gases that we only see that don't react with anything. The only exception to that would be like mercury gas, but I think it's pretty safe to say that they're not going to be asking us about this in this problem. So we know that they're one of these gases, and it's actually more likely to be one of these gases closer to the end, argon, krypton, or xenon, because helium and neon are really, really tough to be able to get to react because they actually have a much tighter hold on their electrons. Versus krypton, xenon, and argon have all been made into compounds using a variety of methods. And so immediately we're told that X reacts with Y to form compound A, and to do this we need electric discharge, which means we are pretty much forcing this reaction to happen. It's not happening of its own accord. And same thing with the reaction of Z with fluorine, or with gas Y, which is fluorine gas, and I'll explain that in a moment. We use ultraviolet light and heat. So we're again sort of forcing it to happen, but light and heat is more of a catalyst to the reaction rather than actually just forcing the electron forward, and this produces three different products. So the reason we know this is F2 is because we need the most powerful oxidizer to be able to actually react directly gas on gas with these two types of gases. Because they're noble gases, they're not going to react with just anything. They're going to need something that's incredibly, incredibly powerful. And really, the only gas that we have, gas at room temperature that we're told, is um, is fluorine gas, and that's actually the main way that we get a lot of these compounds that have noble gases. So it's pretty easy to see that why it's going to be F2. So that means we're looking for a reaction between X and F2 to get A, and Z and F2 to get these three different products. And notice that the reaction with X has significantly stronger conditions. We're using this electric discharge rather than just using light as a catalyst. The next reaction we're told about is the reaction of X and F2, which we can go ahead and guess that it's just going to be XF2. It could in theory also be XF4, but in that case we would also get as a product XF2. So since they're telling us only one product is produced, we can assume that this is going to be XF2. And then we're reacting it with a Lewis acid like SBF5 or BBr3, a really strong one, and we're getting two different cations, B and C. And we immediately know, since we're producing a cation, essentially what this Lewis acid must be doing is it's accepting a fluorine, subtracting that fluorine, or actually a fluoride, from this chemical. And so that's why we're getting, obviously the other product has to be the counterion, which in this case is going to be the Lewis acid as an adduct with the fluoride ion. And so we get two different cations, and obviously the most obvious thing that comes to mind would be if it extracts a fluorine, we just get XF+. So that's probably one of these. Then we're also told that C is about 2.185 times as massive as B. Now 2.185 is pretty close to 2, so we can sort of guess that the formula of C is pretty similar to the formula of 2B. So 2B, if we're assuming that B is the lighter one, we can go ahead and take a guess that B is going to be XF+. Again, we're not really sure, but throughout this problem I'm going to make a lot of assumptions, and the reason I'm doing that is because when I was solving it originally, really what you have to do is just make a lot of assumptions, and if you don't get to a good answer after that, you go back and change the assumptions you make until you get a good answer. So if we assume that C is similar to 2B, 2B is going to be X2F2 2+. But notice that we're we're given that it's C+, which means it has a +1 charge, so we can add another fluoride ion back, and we get X2F3+, which could very well be the identity of C, because it's a little bit more than twice as massive as B. So if we go ahead and plug in this as a formula using this mass ratio that they give us, we can plug in and we can actually solve for the molar mass of X if we assume that this is the correct answer here. And if we go ahead and solve that, we actually get that X is going to be 83.7 grams per mole, and lo and behold, that matches up exactly with the molar mass of krypton. So that tells us immediately our answers to the first few results right here. So X is going to be krypton, A is going to be krypton difluoride, B is going to be KrF+, and C+, is going to be Kr2F3+. So our next reaction is a lot more interesting. We're getting this reaction between KrF2 and some metal M. We're told that this gives us compound D, which contains cation B. So, and we're also told that it produces krypton gas. So, since it produces krypton gas, we know that krypton is getting reduced, and that must mean that our metal M is getting oxidized. Since this metal is getting oxidized, that means the metal is going to have a positive charge. However, we know that the metal is going to be part of the anion because we know what the cation is already. So the only way for the anion to have negative charge, we must have this this metal being bonded to a bunch of fluoride ligands. So that means we're going to have some combination of KrF plus some number of these ions combined with our metal in the +5 oxidation state, and then a bunch of fluoride ligands. And then we're also told that D can be heated, and it'll release Kr, it'll release F2, and it'll release E. And E is a compound that contains M as well, and we can go ahead and actually make an assumption here that if we reorganize all these fluoride ions from this anion to the cation, we would get a bunch of KrF2 units, which decomposes directly to KrF2. So we can actually assume that E is going to be pretty much the same formula as this anion. It may have less or more fluorides, obviously, because of the negative charge, but it's going to be essentially the same compound here. So, first of all, we know that M plus 5, and then however many fluoride ions we have here, has to have a negative charge. So we know that N here has to be greater than 0, because we have to have at least 5 fluorides just to balance out the positive charge, plus an extra one to give us a negative charge. But if N is greater than 1 in this case, then M will have more than 6 ligands, which means it's really, really unlikely to form. The only time we see these sort of hypervalent metal complexes is maybe in water, when we have 8 or 9 coordinate complexes. But generally, we're only going to see up to 6. So we can go ahead and guess that N equals 1. And for this, we can use the formula that they gave us. They told us the mass percent of M. So we can know that the formula is KrF times, and then M and F6. So we can go ahead and calculate, plug in the molar mass of M here, and solve for the molar mass of M if we assume that this is the formula right here. And we actually get a very well-known metal here. We actually get gold as our metal with a molar mass of about 197 grams per mole. And this works out quite nicely because they told us that it was in a rare +5 oxidation state, and gold is typically not found in the +5 oxidation state because it's so noble. Next, we know that it's going to decompose into Kr, F2, and E. Now, if E isn't just gold metal, it has to be a gold fluoride. So we can just go ahead and use the mass percent of gold, which was given to be 67.47%. We can plug in again, and we can solve for the number of fluorines in the compound, and we get N equals 5, which means that E is AuF. So now that we have gone ahead and actually moved through the entire first paragraph, we can start working on the second paragraph here, which is when we start looking at element Z. So notice that Z, we're reacting it with F2 again, and we're doing this with ultraviolet light and heat, which is considerably, it's pretty strong conditions, but they're considerably weaker than using electricity to just force the reaction to happen. So we know that Z is going to be more reactive than krypton. And in addition to this, we see F, G, and H, we see different products, which means that some of these products are going to have a higher degree of fluorination, meaning we're going to see, rather than just ZF2, we're going to see ZF4 and maybe ZF6, some sort of different compounds like this. And since we have this higher level of fluorination, we also have a higher oxidation state, which means, again, that this Z is much more reactive than krypton. So going down the periodic table, we get elements that are more reactive, and going up, we get less reactive. There's obviously some exceptions there with our noble metals, but that's the general case, and that is also the case for the noble gases. So that means that the only one that we can actually have here is Xe, since radon or whatever it is really just not stable enough. So that means our identity of Z is Xe. This means that F, G, and H have to be XeF2, XeF4, and XeF6. Now figuring out which is a little bit difficult because we know, but they tell us that Xe plus G in a 1-to-1 molar ratio is going to give us F. And if we go ahead and plug in what the formula of G is, which is just XeF2n, we realize that F is going to have half as many fluorines as G did, which tells us that G must have an even number, or must have a multiple of 4 in terms of the number of fluorines, which tells us that G has to be XeF4, F has to be XeF2, and H has to be XeF6. Now moving on to paragraph 3, we start talking about this superacid. Now, this paragraph might be kind of difficult if you're not familiar with any superacids, but we can actually sort of figure this out using some reasoning as we go from here. So we're told that J is a hydrolysis product of XeF6, which was H, and H2O. So the hydrolysis product of this is going to be HF and XeO3, and also partial hydrolysis will give us stuff like XeOF4 or XeO2F2. And none of these compounds are going to be very useful in reacting with other things since they're, they'll decompose pretty easily, but in terms of reacting to form adducts and stuff like that, we're probably not going to see these compounds reacting. So it's a pretty safe bet to say that our more acidic compound here, which is hydrogen fluoride, is going to be our J. And we'll go ahead and see this real quick. Next, we know that KrF2 plus our molecule K is going to give us a salt which contains the cation B+. Now, this salt that contains the cation B+, that's exactly the same reaction that we were told about in the beginning, where actually we're told that KrF2 reacts with Lewis acids to form KrF+ and an anion as well. So this really is just telling us that K is a Lewis acid, and the anion in this formula is that Lewis acid plus a fluoride ion. So we can go ahead and solve for the mass of this anion here pretty easily, and we get that the mass is very, very large. It's 235.79, which means that it probably has some super heavy element in it in one of the later periods. Now, we can go ahead and take a wild guess here and assume that it's going to be this element combined with a bunch of fluorine atoms. And that seems like a bit of a stretch, but again, you sort of just have to play around with these problems and make a few guesses before you can actually get to the answer. So if it has one fluorine, we're getting that the molar mass is going to be 216.75, which just doesn't match up. If it has two fluorines, we're getting that the anion here is going to have a molar mass of 197.79, which would tell us it's AuF2-, which would essentially be the compound AuF accepting a fluoride from KrF2. However, remember, we actually need a very strong Lewis acid to react with KrF2 and accept that fluoride. And in the case of AuF, it's really not, it's got most of its orbitals filled, and it's not really a strong Lewis acid that's going to be able to accept a fluoride ion. Then if we assume n equals 3, we get HFF3-, which just does not work out with the oxidation state of HF. It's just not common. It's probably not what we're looking at. If we set n equals 5, we get CeF5-, and again, CeF4 in theory can work as a Lewis acid, but it's just not going to be strong enough to rip that fluoride away from KrF2. However, when we get to n equals 6, we get that our anion, or our other element here is going to have a molar mass of 121.79, which matches up perfectly with antimony, which gives our anion being SbF6-, and it turns out that SbF5 is pretty famous in that it's an incredibly strong Lewis acid. It'll accept a fluoride ion from basically anything. So, this tells us our identities of J and K. We know that J is HF and K is SbF5, and the reaction they're telling us about is the reaction with hydrogen fluoride and SbF5 to form fluoroantimonic acid. Now, notice I put here just SBF5 accepting a single fluoride from H2F. In reality, the situation is a lot more complicated. When you mix J and K, you get a mixture of a ton of different types of species, including fluoride ions, bifluoride ions, these fluoronium ions, and some like weird chains of antimony pentafluorides. So this is sort of just a simplified version of what fluoroantimonic acid actually is. We're now moving into the last part of our problem, and this is with our one really, really complex reaction that we have here. So in this reaction, we have xenon gas adding to our fluoroantimonic acid, which I've just written here as HSBF6, reacting with compound N to form this compound O, which has one Xe signal, which means that there's only one type of xenon atom chemically in this compound. We're also told that gold is in a weird oxidation state, a not normal oxidation state, and that this complex has an overall charge of +2. Then our compound P has 22.86% Xe and has Xe in a plus 0.5 oxidation state, and we also probably have some other leftover products. So first we have to find out what this compound N is. We know that it's 77.56% gold, and a good guess to just go ahead from what all the other things have been in this problem is just to guess that this is a gold fluoride. And it turns out that when we assume that this is a gold fluoride, we get that it's a gold fluoride AuF3, looking at the mass percent here. So now, one thing to notice here is we want to figure out the oxidation state of Au at the end here. We're told that it's a very rare oxidation state for gold. And there's actually one more piece of information here. We notice that xenon gas is actually oxidized to the plus 0.5 oxidation state, which means that gold must be reduced, meaning it's in a higher state, or in a lower state, I should say, than +3. So it has to actually have a state of +2, because if it had a state of +1 or 0 or anything lower than that, then this complex would not be able to have an overall charge of +2, because you can only have negatively charged or neutral ligands when you're forming a complex like that, because otherwise the electrostatic attractions just won't work out for you. So gold has to be in a +2 oxidation state, and all our ligands have to be neutral. And this is actually a really useful piece of information, because knowing that all these ligands are neutral, we only have a few neutral species in our reactants. In fact, the only ones that can really work here would be xenon or antimony pentafluoride, because if we had HF bonding on there, then we would just see that the fluoride would probably give up that hydrogen atom, would give up that proton, and so that would just not be a good product. And for the same reason, basically, antimony pentafluoride is so acidic that it probably won't be a very good base. And so in this case, we're not going to really see the fluorine atoms bonding to the gold, which means that the only ligand that we can have here is xenon, which sounds super weird, but this tells us that our cation is gold. I don't even know how you would say this, but it's Au2 plus with 4 xenon ligands, which is absolutely wild. Now, to calculate the mass of our anion, we can go ahead and use our mass percent, which we know the mass percent of Xe, since we're given that. This tells us that the overall mass of our anion is 904.73 grams per mole, which is a huge, huge, huge number. This tells us that we have really massive anions. But more importantly, it tells us we can see that this is pretty close, like in the general area of 4 times the mass of SBF5. And so this is where it comes in handy to know a little bit more about the superacid antimony pentafluoride, because in a fluoroantimonic acid, we get SBF5 combining with SBF6 minus to create these sort of like linked chains of antimony pentafluoride. We get Sb2F11 minus, Sb3F16 minus, etc., etc. Since we have a 2 minus charge, you can sort of play around with the charges and the different anions. But it turns out that Sb2F11 minus is a nice anion, and if we take 2 of those, we get roughly 4 times the mass of SBF5. And if we check the molar mass, we get 905.04, which is close enough to 904.73, which we calculated right here, to probably be our answer. So this is the anion, which absolutely seems wild. This tells us that compound O is AuXe42+, combined with sp2f11 minus 2. As for our other product, compound P, since we know Xe is in a plus 0 0.5 oxidation state, we can assume we're going to have an Xe2 plus ion. That's just an assumption we're going to make here. And we can calculate the mass of the anion here using the same method. We get a pretty similar mass, just a little bit less, and we actually notice that it's the same mass as our other anion if you subtract 19, so you're getting rid of one fluorine, or in this case one fluoride. And this matches up perfectly with Sb4F22 2 minus, which is just adding two of these together and then just subtracting one of those fluoride ions. So Sb4F21 minus. You can think of this as 3 units of SbF5 and 1 unit of SbF6, sort of all bonded together in a chain. So this is our anion for our compound P, which means that P is Xe2Sb4F21, which I think is so funny. And this is actually the entire problem. This problem took me about an hour and 20 minutes, maybe an hour and a half to solve overall. Obviously, I used my periodic table and I was just mashing a lot of numbers, but I think this problem was a lot of fun. I think if you do chemistry, you should definitely try some of these problems since they're really good just to help your critical thinking in general and also to help with just sort of understanding chemistry a little better. So here are all the answers. I'm not going to go ahead and write out all the balanced equations, but if you guys want to do that, to write out the balanced equations for all the reactions, go ahead. Anyway, thanks for watching. I hope you enjoyed the video, and I'll see you next time.